Let me move on to talk about the advanced inequalities because I think these will be a little bit newer to many of you. I want to talk about two sets of inequalities. One is called the Chebyshev bound. The other one is called the Hoeffding bound. So to start with, let me comment on this. Okay, we are looking at the probability of this bad event. Now, this bad event involves an absolute value. This absolute value is actually not fun to deal with. And so what we can do is that we can write it in terms of the order of two events. The first event is that nu minus mu is bigger than epsilon. The other one is nu minus mu is less than minus epsilon. So what you can view it is this. Here is your distribution. It doesn't need to be Gaussian. It could be something. And then you're drawing two tails. And then here is minus epsilon. And then this is plus epsilon. And then you're asking, what is the probability of having this bad event? Well, the bad event is defined as these two, the sum of these two events. And so you have, you can write this or, bigger than epsilon or less than minus epsilon. Then you can apply the union bound to get the upper bound on these two. So you get, one event and the other event. If these two events, they are, if these two events, they're destroyed, then you get E equals sign. Okay. Otherwise, you, in general, just apply the union bound to get, the upper bound here. If each one is A, then of course you have 2A. Okay. And now, of course, we need to discuss what is the exact value of this A. But here I can show you that all I need to do is just to look at one-sided inequality, and then I just double up, then I will be able to bound this quantity here. The main result that we are going to derive is called the Hoeffding inequality. The result is given by this, is the probability that nu minus mu bigger than epsilon is upper bounded by 2 times e to the power minus 2 epsilon squared n. This is a little bit complicated. I need to explain the intuition here before we move on to the derivation. So you look at this inequality. This is in the same form as the Chebyshev. You have a left-hand side, you have a bad event, and then you have right-hand side, you have an upper bound. Okay, so same thing. Now, let's look at this upper bound here. This upper bound says that I have a constant 2, which we can talk about that later. And then we have this minus 2 epsilon squared n. So let's fix the epsilon squared. That's my tolerance level. I have the choice. I fix it, okay, to be some number. Then as n going to infinity, what will happen to this exponential number? As n going to infinity, this is e to the power minus n, that will go to 0. Is it faster or slower than the Chebyshev bound? It has to be a lot faster. It's actually way faster than the Chebyshev bound. So when you go back to the diagram I showed you before, here, you can see that this is the actual experiment that we will be able to get from our computer. Chebyshev is just too slow. And so with this result, at least I can see that there is a hope that I will be able to catch this trend. Okay? So that is the direction that we're going to, because we want to have an exponentially decaying bound as a function of n, that as n going to infinity, this will go to 0 very rapidly. Okay? So if I can show that, then I can have a very tight bound for the diagram that I've shown you before. Okay, so now we can deal with this 2 here. So you can ask, what happens if my epsilon is very small and my n is also very small, so small that they're so close to 0? Okay, then you have a 2 times something, then you 2 times 1, then you have 2. Then isn't it just the probability is less than 2? Isn't it? How can that be possible? Because all the probability will be less than equal to 1. Well, the argument is that, yes, as n and epsilon, they're going to very small numbers, this upper bound will become 2. You're correct. You're absolutely correct. But the 2 is still a legitimate upper bound of the probability, because probability is upper bound by 1. It's still correct. Nothing is wrong. Okay. So now, you can ask, then that means your upper bound is not tight. You are also absolutely correct. The upper bound is not tight when n is small. The upper bound is only tight when n is extremely big. Okay? This is a set of results known as the asymptotic results. They're also called the large sample results, which only applies when n is extremely big. Okay? How big? Well, think about at least 1,000 or 10,000, or if you want, you can think it as 1,000,000. Okay, n has to be extremely big in order for this inequality to be true. Okay, now when n is small, this is still okay. It's still a legitimate bound, still a valid bound, but it's just not very informative to the purpose that we want to use it. Okay, now can you make this epsilon extremely small too? No, you will never try to make the epsilon really small because you care about the bad event. If epsilon is really, really small, then what are the bad events? Your bad event seems to be too big, right? So you don't want the bad event to be too big. And so you're considering an extremely small tail. You want to ask, what is the probability that I will have a catastrophic failure, okay, on the two tails? And so epsilon normally is big, and also the n usually is big, and therefore this bound is usually tight. Okay. Now you can also show that this Hoeffding inequality is really a tight bound for the set of random variables, where this random variable is lying between 0 and 1. You probably cannot do better than this Hoeffding bound in terms of the rate of convergence. Okay, so how do you do the Hoeffding inequality? We might not be able to finish all the discussions today, but let me show you the outline, and then we can come back to the derivation on Wednesday. So the idea is the following. There's only one key idea. The key idea is in the second line of this page. So let's look at the one-sided inequality, because we now know that you can divide the two events into two, okay, one less than, one bigger than. So let's look at one case. And then let's write out this expression. Here is your empirical average, and this is the definition. And then we can move around the terms so that this n will go to the two sides. Okay, so now the n will go to the epsilon n, and you also have the summation of the mu's. Then here is a very, very important trick. Okay, this is the single most important trick here, is that you go to this equation, and then you take the exponential on both sides. Okay, you will say, why do you want to do that? Okay, what makes you consider that? Don't ask me that yet. Okay, I will explain it later. But let's just take the exponential on both sides, e to the power something and e to the power something. In addition, I'm also introducing a variable called s, where when I take the exponential, I have e to the power s something, e to the power s something. That s is just a number. It's a parameter. It's a hyperparameter that I put in. Okay, so once you do that, then you can apply a thing called the Markov inequality. Now, why cannot I apply Markov inequality directly to here? You cannot do that because this quantity can be negative, because you're taking the empirical average minus the true average. Okay, so the empirical average could be less than the true average. So the Markov inequality, the assumption that the random variable itself has to be positive, does not work here. But once you put the e to the power s something, both sides, they are non-negative, so you're good to go with the Markov inequality. So you apply the Markov inequality, then you have less than or equals to this divided by that. Okay, and then now you can also do some small trick based on the independence. You can pull out the n. Then you are left with this quantity. Okay, and you can see this quantity doesn't really seem to provide you any information. However, if you recall whatever you have learned from your undergraduate probability, the numerator is actually the moment generating function of the random variable xn. Okay, so this, let me tell you, this e to the power s of xn minus mu is the moment generating function of this zn, where zn is xn minus mu. Okay, so moment generating function. Now, if you don't remember the definition of moment generating function, you can look at the undergraduate textbooks. Okay, so because this is the moment generating function of a random variable, you can actually derive upper bounds on these moment generating functions. Okay, so what we are going to do is that we're going to look at this inequality. Okay, so this is Markov inequality applied to this moment generating function. As long as I can upper bound my moment generating function, do we agree that then I can have a bound on this quantity? If I only apply this by 2, I will get the overall Hoeffding inequality I want. Okay? So the whole logic in this derivation is to do this E trick and also apply the Markov inequality. Then the rest is just to apply some standard known results in the probability literature in finding the upper bound on the moment generating function. Okay, so let's skip some of these discussions by just showing you the results. So this lemma is called the Hoeffding Lemma. They show that the moment generating function is upper bound by this quantity, and therefore when we go to the very end, we can go to this result. Okay. Now, of course, I'm skipping some of the derivations, which we will look at them next time. However, you can see that this result is really just applied by using the moment generating upper bound. And here's the curve that you will expect to see when you try to do the experiment. This is the red curve, that's the Chebyshev curve, and the blue curve is the Hoeffding bound. Okay? Again, this is my cartoon drawing, but you can also program it on Python and MATLAB. You will be able to see the same pattern here. Okay. Just draw a Bernoulli coin flip 1,000 times, 10,000 times, 1,000,000 times. As the number of times goes up, draw the green crosses and then draw the blue lines, and then you will be able to see the Hoeffding inequality is a lot tighter. Okay, so a couple comments on how they can be useful. So you can compare these two. On the left-hand side, we have the Chebyshev inequality. On the right-hand side, we have the Hoeffding inequality. So they are both in terms of this. They're both in terms of the probability is less than certain number delta. As I said, delta would be a number that you want to control. Okay, and normally you want this delta to be small, and you ask which one is smaller for the given n, and certainly this one is smaller. Okay, and now for this, you can also say that for probability at least 1 minus delta, we have this nu living on this confidence interval, where mu is minus epsilon and mu is plus epsilon. And so this epsilon is going to give you certain confidence interval error bar surrounding your estimate. Okay, and here you can show that for Chebyshev inequality, your epsilon is sigma divided by this delta times n, and then here your epsilon is given by that quantity. And here this is decaying as a function of square root of n, and this is also decaying as a square root function of n. But however, you have a log term here, and so this log term has a different impact on this epsilon that you have. Okay, so let's also briefly talk about the number of samples, which we will also visit them again next time. Is that once you have this inequality for Chebyshev and also for the Hoeffding inequality, you have these two confidence intervals. You can say, what if I put delta equals to this number and then n equals to this number and sigma equals to 1? What would be the epsilon? The epsilon here will be a lot smaller, so you have a lot tighter confidence interval. Versus the other case is that you give delta, you give epsilon, you give sigma. You ask, what is the number of training samples that I need in order to reach the level of confidence? Then here for Chebyshev, you need 1,000,000, but then for the Hoeffding bound, you just need 26,000 samples. Okay, according to the probability upper bound. Now, which one is better? I would say that this is just too conservative. Okay, if you go to this number, of course that would work. Okay, but the Hoeffding says that even with this small number, you will still get to the poor tolerance level that you want. Okay, this is just overkill your performance. Okay, all right. So please go home and take a look at the derivations, and then we will revisit them again next lecture, and then we'll move on to draw the connections with the learning theory that we have been discussing so far.